Welcome back. In this video, we're going to be looking at applications of linear programming. So the example that we're going to look at is a manufacturing company receives orders for engines from two assembly plants. Plant 1 needs at least 40 engines, and Plant 2 needs at least 30 engines. The company can send at most 145 engines to these assembly plants. It costs $50 per engine to ship to Plant 1 and $55 per engine to ship to Plant 2. Plant 1 gives the manufacturing company $20 in rebates toward its products for each engine they buy, while Plant 2 gives similar $10 in rebates. The manufacturer estimates that they need at least $1,500 in rebates to cover products that they plan to buy from these two plants. We want to know how many engines should be shipped to each plant to minimize shipping costs, and then we want to know the minimum shipping cost. All right. So, the first thing we want to do on any problem like this is to define our variables. So we need to know what it is we're solving for. It's really tempting to skip this step, but it's really, really important to be able to know what the things are we're solving for. So let's look at the question part here. It says how many engines should be shipped to each plant to minimize shipping costs. So let's let x equal the number of engines to be shipped to Plant 1 and y equal the number of engines to be shipped to Plant 2. Again, we always want to include units here. So we don't want to just write x equals Plant 1 and y equals Plant 2 because that's not going to give us enough information. X is the number of engines to be sent to Plant 1, and Y is the number of engines to be sent to Plant 2. This is going to be really important when we start writing our inequalities. All right, now the next step on problems like this is we notice that we are looking for the minimum shipping cost. So this is really important because this is what's going to distinguish this type of a problem from a linear system of equations. With linear systems of equations, there's either one answer, so a unique solution, there's infinitely many solutions, or no solution. There's no room for a minimum or maximum solution. And here, there is a minimum or maximum solution, so that tells us that we're working with inequalities and not equations. So, what we want to do here is we want to write out our objective function. And I would start with your objective function after we define our variables because it's easy to forget about. So always start with your objective function. Look for the thing we're trying to minimize or maximize. In this case, it is cost. So I'm going to write this as we want to find the minimum. We want to find the minimum cost. So we're going to write min C. Minimize C. And so what we're looking for, we're wanting to minimize the shipping costs. So let's look up in our problem and find our shipping cost numbers. It says it costs $50 per engine to ship to Plant 1 and $55 per engine to ship to Plant 2. So those are our shipping costs. So it's $50 per engine to ship to Plant 1, and X is the number of engines being sent to Plant 1. So that's $50 times the number of engines, or 50x. And then $55 per engine to ship to Plant 2, and number of engines shipped to Plant 2 is Y. So that's going to be plus 55y. So we've used those two numbers, the shipping cost numbers. All right, now that we have our objective equation, we can go ahead and look for our inequalities. The way we want to start our inequalities is to first start with the number on the right-hand side, the constant or the total. That makes it quite a bit easier. I'm going to go over real quick a common mistake I see here, and then we'll go over why it's a common mistake. So when people start reading through this problem, they typically, or will frequently read this as Plant 1 needs at least 40 engines. All right, so Plant 1, 40 engines, that's 40x. Plant 2 needs at least 30 engines. Okay, so Plant 2 is Y, so that's 30y. And the company can send at most 145 engines. Okay, so at most, that's less than or equal to 145. All right, so that's the inequality that we would get if we didn't actually think through what this means and we didn't actually pay close enough attention to what our variables are. So let's look through this. So 40 here, that is the number of engines to be sent to plant 1. X is the number of engines to be sent to plant 1. If we multiply those together, our units would then be engines squared, which is not a unit that is going to be helpful to us. Same thing here. That's number of engines to plant 2, the 30, and the Y also number of engines shipped to plant 2. So again, we would have engines squared. So this inequality doesn't really make any sense and is not correct. So erase that or cross it out or something like that. All right, now what we want to do here is we want to look through this and we want to look for inequality phrases. Those are going to help us because every time we see an inequality phrase, that's going to tell us that we have a new inequality. So plant 1 needs at least 40 engines. Okay, so I see the word at least 40. All right, so without even knowing anything else, I know something is going to be greater than or equal to 40 engines. Okay, I don't need to know anything else for right now. I know something is at least 40 engines. At least is greater than or equal to. All right, now that I have that part, now let's figure out what goes on the left-hand side. What is at least 40 engines? And it says plant 1 needs at least 40 engines. So this has nothing to do with plant 2. It is simply the number of engines shipped to plant 1 needs to be at least 40. Well, the number of engines shipped to plant 1 is X. So this is just X is greater than or equal to 40. This is another reason why it's really important to always define your variables. All right, keep reading. Look for our next inequality phrase, at least 30 engines. Okay, so greater than or equal to 30 engines. All right, so again, easy enough. We don't need to understand anything else. We just need to find inequality phrase and then a number. So at least 30 engines. All right, now we can look back and see what should be to the left of that. And it says plant 2 needs at least 30 engines. So that should be the number of engines shipped to plant 2 is greater than or equal to 30. Or in this case, Y is greater than or equal to 30, since Y is the number of engines we're going to ship to plant 2. All right, so we keep reading. The company can send at most 145 engines. Okay, so at most 145. So at most, that's less than or equal to. So less than or equal to 145 engines. All right, what is at most 145 engines? So it's the company can send at most 145 engines to these assembly plants. So that's plural, plants. So to the 2 of them. Right? So to the 2 plants combined, the number of engines combined sent to these 2 companies needs to be less than or equal to 145. Well, the combined number of engines, that's X plus Y. Number of engines sent to plant 1 plus the number of engines sent to plant 2 needs to be less than or equal to 145 because that's the most they can send. All right, let's keep going. Keep reading, looking for inequality phrases. All right, our next one, at least $1,500. All right, so at least, that's greater than or equal to $1,500. Now, we do need to be careful here because there's 2 different dollar figures in this problem. We have the dollar figures for shipping costs and then the dollar figures in rebates. So we want to make sure we kind of separate those out. We've already used the ones for shipping costs. Those are highlighted in yellow. So we just want to deal with the rebate dollar figures. All right, so plant 1 gives $20 per engine. So that's 20 times the number of engines shipped to plant 1, which is X. So that's 20X. And then plant 2 gives $10 in rebates. So that's $10 per engine, where the number of engines is Y. So that's going to be plus 10Y is greater than or equal to $1,500. All right. so as we keep reading, we don't see any more inequality phrases. So these are all of our inequalities. Well, actually, not quite yet. We have 2 more inequalities that we will need for every word problem, and that is that x and y need to be greater than or equal to 0. Now, it doesn't tell us that, but could we ship a negative number of engines? No, that wouldn't make any sense. So x and y need to be greater than or equal to 0. Now, that's going to be a little redundant on this problem because x needs to be greater than or equal to 40 and y needs to be greater than or equal to 30. So already they're going to be greater than or equal to 0. But we want to write that for every word problem. That's going to be really, really important. And if you forget that on a word problem, it's likely going to throw you off. So make sure you have the 3 parts to every linear inequality problem. That is, you need your objective equation. So that's our minimum C equals 50x plus 55y. The constraints, those are the next 4. And then the non-negative constraints. So always those 3 things, every single word problem where we are trying to minimize or maximize something. All right, now that we have all of that done, we can start the process of finding our minimum by solving our inequalities for y. That way we can graph them, find the feasible region, then find our corner points, then find our minimum. So let's start with x plus y less than or equal to 145. We'll subtract x from both sides. So we'll get y less than or equal to negative x plus 145. We'll call that one y1. We'll make that one blue equation. We've then got 20x plus 10y greater than or equal to 1500. So we will subtract 20x from both sides. So that's going to give us 10y greater than or equal to negative 20x plus 1500. And then we'll divide both sides by 10. That's going to give us y is greater than or equal to negative 2x plus 150. Call that one y2. We'll make that one green. We have a y3. y3 is y is greater than or equal to 30. We'll make that one the red equation. And then we also have x is greater than or equal to 40. That one's not one we're going to be able to graph with our graphing calculator, but that's okay. We'll account for it when we draw it out. We also have x and y greater than or equal to 0. That's going to be our x and y axis. So we'll know those on our graphing calculator as well. All right, so let's get these into the graphing calculator and see what our graph looks like. All right, I've gone ahead and already put these in. So negative x plus 145, negative 2x plus 150, and then 30. All right, so when we graph these, when you graph these, you'll need to zoom out twice to be able to get to where you've got the screen that I can see here. But if you start at zoom standard and then zoom out twice, it should look exactly like what I have on the screen here. All right, so what we want to do is we want to draw this out. So we can do that, but first we need to figure out where x greater than or equal to 40 is. So if we use our arrow keys and just start going right, we can see down here at the bottom left, we can see our x value. So I'm just going to go until I get to 40, or as close to 40 as I can get. Okay, I can get right on 40. So what we want to do, the line x equals 40 is a vertical line. So it would pass through where we can see our cursor there. So the important thing here is that vertical line would cross this line first. That one's going to be y1. Then it would cross y2. And then it would cross y3 and then the x-axis. So we just need it to cross in that order. So let's go ahead and draw all of this out. All right, so on our calculator, if we hit the trace button, we can see which line is which. So the line here, the line y1, we can see that one, and y2 crosses it and goes under it. So we'll start with y1, which looks about like that. And then y2 crosses it and goes about like that. Oops, y2 was supposed to be green, so let's change that to a green line. There we go. And then our y3 was red. So that is that horizontal line right there. All right, let's go ahead and label these. So y3, y2, and y1. All right, then we also need x is greater than or equal to 40. We saw that 40 was about right here. It doesn't really matter if you get it in the exact right spot. Really, as long as it's to the right of this intersection point where y1 and y2 intersect, and to the left of this intersection point where y2 and y3 intersect, anywhere in between there is going to be just fine. All right, so now let's look back at our inequalities. y1 is less than or equal to, y2 and 3 are greater than or equal to. All right, so y1 less than or equal to, we're just going to shade just a little bit below it just so we can kind of get a good idea. And then y2 and 3 are greater than or equal to. So y2 will shade above that line. And then y3 will shade above that line. And then also our x greater than or equal to 40 will shade to the right of that line as well. And then we also know x and y need to be greater than or equal to 0. Which they're going to be because x has to be greater than or equal to 40, y has to be greater than or equal to 30. All right. So what we can see here is that our feasible region is this region right here. It is above y3, above y2, and below y1. So that region is our feasible region. It satisfies all of our linear inequalities. All right, so our corner points would be the intersections on this feasible region. So we have 4 of them. We have where y1 and y2 intersect x equals 40, and we have where y1 and y2 intersect y equals 30. Now, there's a couple different ways we can find these points. The ones that intersect y3, those we could find with the intersect function on our calculator. The other 2 we can't because we didn't draw that line with our calculator, but that's okay. It's pretty easy to solve for all of these. We can actually do all of them without the calculator fairly easily. All right, so let's rewrite y1, y2 real quick. So y1 was y1 is less than or equal to negative x plus 145, and y2 was y2 is greater than or equal to negative 2x plus 150. Our x line, that was x greater than or equal to 40. And then y3, that was y3 greater than or equal to 30. All right, and then let's rewrite our objective function as well. Z equals 50x plus 55y. Okay. All right, so one of the things that we know about these points, we actually know one thing about every single one of these points. So these 2 on the x-axis, or on the line x equals 40, we know the y values. Both y values are 40. Because if they're on the line x equals 40, they have to be 40. So we can solve for y on each of those pretty easily just by plugging 40 in for x. So with y1, that's y equals negative 40 plus 145. And that's going to give us 105. And then we'll plug in 40 into y2. So that's y equals negative 2 times 40 plus 150. So negative 2 times 40, that's negative 80. plus 150, that's going to give us 70. So that one is 40, 70. All right, the next 2 points, we can do the same thing with y1 and y2. We'll just plug in 30 for the y value instead of plugging something in for the x value, because these points, we know what the y value is. So both of these have y values of 30. All right, so we've got, for y1, that's going to be this one right here. y1, which actually we're plugging y in for that, so that's going to be 30 equals negative x plus 145. So I'll subtract 145 from both sides. We'll get negative 115 equals negative x, or x equals 115. So that's our x value there. And then for y2, that's 30 equals negative 2x plus 150. We'll subtract 150 from both sides, so negative 120 equals negative 2x. Divide by negative 2, that gives us 60 equals x. So our x value is 60. Again, we could have used the intersect function on our calculator to find those two, but it's not terribly difficult when we're finding lines, when we're finding points on a vertical line or a horizontal line. All right, last step is we just plug these values into our z equation to figure out which one is the smallest, because we were trying to minimize, actually it wasn't z, it was c, sorry about that. C for cost, because we wanted to find the minimum cost. We often call it z as well, but it really doesn't matter what letter you use, it's just the thing we're trying to solve for. All right, so if we plug 40 in for x and 105 in for y, we get 7,775. So that is the cost to ship 40 engines to plant 1 and 105 engines to plant 2. 40/70, that would be 40 engines to plant 1, 70 engines to plant 2. So we plug 40 in for x, 70 in for y into our cost equation. That's going to give us 5,850. All right, 60/30, when we plug that in, 60 in for x, 30 in for y, we get 4,650. And then 115 and 30, 115 in for x, 30 in for y, we get $7,400. All right, so our minimum shipping cost is $4,650. That's the smallest of those four. So that is our answer. They should ship 60 engines to plant 1, 30 engines to plant 2, which will cost them $4,650 in shipping costs, but that is the minimum amount they could spend on shipping while still meeting all of the other constraints. All right, so that's it for linear programming. So just to recap real quick, we defined our variables. We wrote our inequalities starting with the right-hand side. So we looked for those inequality phrases, at least, at most, those sorts of things. We then wrote our inequalities. We solved them for y, graphed them, shaded, found our feasible region, and then found the corner points of our feasible region. And then we plugged those corner points into our objective equation to find our minimum. All right, that's it for this time. I'll see you next time.